In a recent video on Munro Live, Sandy Munro interviews Thomas Mueller from Wipro, and they get into some really interesting things. Thomas's company reverse engineers a lot of the electronic components that go into vehicles, and he has some amazing insights into why Tesla is so far ahead of the competition. Let's take a look. Hey y'all, it's Dr. Know-It-All. I'm going to play a few of the clips from the 42.5-minute video that Sandy and Thomas did together at CES 2023, probably a couple of weeks ago now, since that would have been it. Anyway, the video just came out a couple of days ago, and I watched it yesterday, and I was like, wow, I've got to do a video where I go into a little bit more detail about these specific things. But anyway, of course, I will put a link to the original video in the description, and you should definitely watch it. It is chock full of really amazing stuff. I'm just going to break out a few small pieces that I personally find particularly interesting. Before we even watch any of the video clips, the title of Munro's piece is 100 million lines of code. It turns out that's how much code is in most modern vehicles. And that demonstrates to me a massive, massive inefficiency. And a lot of what Thomas talks about is the fact that you've got all of these ECUs, or electronic control units, that are floating all over the vehicle. They don't really talk to each other very well, and they're not integrated very well in legacy auto. And that's a place that Tesla and others are beginning to try to figure out how to do this, but Tesla is leaps and bounds ahead of this. With that in mind, around the 9-minute mark, Thomas starts to talk about how Tesla uses the second redundant hardware chip on hardware 3, the second drive chips that they have on their main board, or what he terms the failover chip, to do other tasks right now. So in other words, you've got this redundant amount of processing power that's going on, this hardware that's there. Normally that would just sit there. That would be a redundant backup in case something fails at the beginning. But instead, what they're able to do is utilize that for driving in shadow mode and for other purposes. And then the failover chip can kick in if the original chip has a problem within a few milliseconds, as he said. And again, because he's reverse engineering this stuff, I would expect that he actually knows this from evidence from having looked inside the chip and looked at the code and how it's all written.
When you tear down their central cockpit computer and ADAS computer, you'll figure that the ADAS computer has two of their own silicons that they design. One is there for live operations, and one is there for backup. Now you can say that's wasteful. From a BOM perspective, it's wasteful to have a standby system just for redundancy. So the smart and very different move that nobody else in the industry so far has really been mimicking or adopting is Tesla started to use the standby chip, the SoC, in normal operations for performing value creation for them as a company, because they basically run a second version of the autopilot software, as they call it, the ADAS software, as we say generally. They run the same copy of it, and that same copy analyzes your driving, your operator of a Tesla. It's called shadow mode. And this shadow mode is a very efficient way of helping Tesla to create better software, like you mentioned before. And this is the main difference. They're not just wasting the resources for standby cases, which are unlike, but they can occur, but they're making actually productive use. And that's very similar to CIOs in their data centers using not just passive standby servers to back up a hot live server, but they're using the standby servers for testing and other purposes, while still having the ability to switch over within a few milliseconds from a live system to a failover system.
So this is a really fascinating insight. This is something where it's become obvious that Tesla does use their second hardware chip to do other activities because of the nature of them. You know, some of the research presentations that I've seen by Andrej Karpathy and later Ashok Elluswamy and other people like that. Anyway, it's become evident that Tesla is definitely utilizing both of the chips, but assuming, of course, that Thomas has actually dug around and looked at the code, it seems like specifically what they're doing is they're using one of those chips to do offline testing. There, right? It can drive in shadow mode, which is basically, if I, as a human being, am driving my Model Y, I'm doing that, and the one chip is doing the vision systems and making sure everything is safe, right? Or it's driving in full self-driving beta, and I'm just monitoring that. So that's what one chip can do. The second chip can be running a test version of the system, and it could be running in shadow mode where it's making predictions. It's like, I think that the car should turn right 5 degrees right now, or I think the car should brake right now, or accelerate right now, or do things like that. So it can make predictions, and then it can grade itself based on what I as a human being do, or what the official version of full self-driving is doing. So that ability to utilize the backup or failover chip instead of just letting it sit there and be redundant, which a lot of companies do. As he says, nobody else is doing this in the auto industry, but instead of just letting it sit there and just, take up space and not do anything useful, it's doing useful work with code that's involved, that if something happens to the initial main chip, that it can flip the failover within milliseconds, and so it can flip and take over when it needs to. So you're not losing any critical functionality, but at the same time, while 99.99% of the time the main chip is working just fine, the backup chip can be doing useful work and learning and submitting data and figuring out a bunch of things. Speaking of which, he then goes on to say a couple of minutes later how the chips are able to sort through data at the edge rather than in the cloud, and why this is so important.
But that's only one part of the equation. The other part of the equation at Tesla's was really to think of a system that is in the vehicle and is able in real time to make a digestion between information that comes in from a camera signal or from a radar signal in earlier days, and say, is this relevant for me to actually bring back to attention at my mothership level, or shall I leave that information and just drop it and discard it? And here's the different approach. The Tesla, I call it the Tesla harvester, is extremely efficient. If you Wireshark the connectivity connection between a Tesla and the information transmitted to Tesla's private cloud, you will figure out that after a 2-hour drive, a Tesla produces a stunningly low amount of data that is being extracted from the vehicle. That is nowhere near close to the overall amount that comes in from the sensor stack. So Tesla, in other words, filters out the needle in a haystack right underneath the passenger seat where the ECU is allocated, the high-performance computer. Other car makers today are approaching this by collecting all of the signals from the radar, from the cameras, storing them, transmitting the bulk load to a central platform, and then trying to figure out the needle in a haystack later on. That not only creates a lot of cost on cloud platforms, the likes of Google, Microsoft, or AWS, it also delays the decision making to see what's relevant and not. Tesla's ability in real time to decide what's relevant or not is the big differentiator.
So this point is really worth focusing on for just a moment. I think it's critical for people to understand, and this is something I didn't know about before. And again, I'm assuming that because he reverse engineers chips, he knows a lot of this information by looking at the code itself. But apparently Tesla's chips actually do, and apparently there's a controller right underneath the driver's seat, which is, I guess, where a lot of that functionality happens. But basically it sorts through the data in close to real time. So as it's sucking in this data, all the vision systems, all of the things that are going on, the decisions it makes, the disengagements that the human driver does, the differences between when shadow mode says that it should be doing one thing and the person does something else. All of those things, it's real-time sifting, or close to real-time, sifting through that data and deciding what's important at the edge being the car, okay? So, edge computing is something like your phone or whatever. It's at the edge. So you've got centralized computing like in a cloud or a big giant server area. And then you've got, sort of in between, which is like a computer or something that connected. And then you've got mobility, and mobility is at the far edge of the computing cloud. And that edge computing takes a load off by sorting and sifting and selecting data at the edge. You have a couple of gigantic wins. Number one, you don't have giant data transmission needs, right? You don't have multiple tens of gigabytes that you have to transmit up to the mothership every single day. That's very expensive. It's expensive for us users because we're transmitting the data ourselves, and but most of us are paying for internet, so we don't really notice that. But on their end, sucking in that terabytes of data, multiple terabytes of data, terabytes, probably not petabytes every day, but anyway, terabytes of data, by sucking in all of that data every single day and putting it someplace, they have to store it. All of that costs money, whether or not they put it on Google servers, or I think Tesla has pretty much all in-house servers. It still costs a lot of money. And And Ashok and other people have talked about how they don't even themselves, I think they have 500 petabytes of storage, at least the last that I heard, but that's not nearly enough for them to store all the data they need. So they always have to keep shoving data out. You know, there's constantly sunsetting data they don't need. But by not pulling in the huge amount of data, but only pulling in just what they need, they can reduce the load on data storage and also on transmission. And then beyond that, they can also reduce their compute loads in the cloud itself, in the servers, the main servers, because the edge computing has already done a lot of the sifting. So that can reduce the amount of time it takes because, of course, these computers have to go through all of this data and figure out the important moments and the things that they need to look at in order to learn better. Those sorts of things have to happen at the main server area, at the mothership, if they don't happen on the edge. So by doing it on the edge, as opposed to having to do it, all of that in the cloud, you're distributing it because, of course, all of these Teslas are computing devices. So you can utilize those computing devices to do a lot of the work, which offloads the work from the main server racks, which means they can focus on other things like doing training runs and stuff. So this is really, really critical. And again, I'm going to assume that he is correct about this because that's what his company does, is they reverse engineer these chips and they look at the software and everything. But, again, assuming that this is correct, this is fantastic news. This means that Tesla is utilizing, between that and utilizing the failover chips, they're basically using all the compute resources in the car actively, which means that they're able to reduce the amount of data that's sent and increase the ability to cycle through this stuff faster by distributing out all the compute to the edge instead of the center of the cloud. This is really, really cool stuff. Next up, Tomas talks about the state of electronic control units, or ECUs, in modern vehicles, again, mostly excluding Tesla, and how bad the whole situation is.
So you need enough horsepower to do this, and this horsepower is relevant for the product lifespan. So the product lifespan is 15 years, presumably, or 12 to 15 years. So how do you ensure that you have enough horsepower from day one to zip through this, as the software that makes sense of this information also keeps growing? And this is where the disaggregation, we call this the disaggregation of the traditional distributed ECUs, and the move to a centralized supercompute platform in a car, which is abstracted from the software itself, becomes so relevant to the industry. So when we speak about teardown analysis, we want to basically take those 150 ECU boxes, take the software out of them, take this software, transform it to a software that can be better maintained. Because it's like, I'm a mainframe guy. I grew up in my early days on an IBM mainframe. It had monolithic code. It was very hard to make changes to that because it had so many impacts.
Right, yeah.
Today, the software in these ECUs is written exactly the same way. It's monolithic spaghetti code. But if you want to transform it to smaller chunks, which can be maintained much easier, like Lego, small Lego bricks that can be composed and decomposed easily, that is where the software gets refactored, the software gets migrated, and can be landed on a platform similar to the likes of Amazon Cloud or Microsoft Cloud in a car. We call it a microservices platform. And this is where software engineers have a huge opportunity in making their life a lot easier. The other thing that I want to touch upon is all that software in a car, these 100 million lines of code today, are written in literally a single language. It's C, a 40-ish year old programming language developed in the late 60s and the early 70s. That software language is used across all car makers. It's very limiting to find people that are really good at it. It's very limiting in terms of security challenges. It's very slow in realizing new use cases. People cannot use modern coding techniques to write the software that is in the car, which is a limiting factor.
So as you can hear from what Tomas talks about, ECUs are kind of their own little kingdoms, right? So each one of these little chips that does something, like something that controls your seat, or something that looks at the ABS braking system, or something that looks in the fuel injection system, or something like that. Each of these little ECUs is both hardware and software. It's its own little fiefdom, right? It's its own little thing, and you order it from whatever supplier it is, and they're the ones who create the code. And again, C, not even C++, C, something that was developed 50 years ago in the 60s and 70s. You get the hardware and you get the code as one unit. And that is what he talks about disaggregating, is separating that out. Because the problem is, let's say you've got this chip and your automobile, you look at this thing and you're like, oh, that doesn't do exactly what we want. Well, how do you fix that? You have to go back to the supplier. You have to ask them to reprogram it. This is a language that not that many people write in anymore, so you need expert coders. It's a pretty boring job. It's not nearly as sexy as a lot of the newer jobs, so it's hard to find good engineers. So, this can take time, and they might just say, sorry, this is what you get, and that's all you got. You use it the way it is, and you make use of it. So you've got a lot of code. Again, he calls it spaghetti code, which contributes to the 100 million lines of code, because there's also repeated code. Every single one of these ECUs has repetitive code in it, which is, bootloading and things like that. There's all of this stuff that just gets repeated over and over and over again. So you've just got this layering and layering of code, and each one of these little chips is basically a piece of hardware. You can't change it, which is the whole advantage of software, is that you can rewrite it and you can update it and all of that kind of stuff very, very rapidly. You can't do that in these situations because the hardware and software is married. So what Tomas is saying here is that you need to separate or disaggregate the software from the hardware, and that's a big step. But the problem is that legacy auto manufacturers haven't figured out how to do that because they order the chips from other people. Now, I would say, looking back at the pandemic and the chip shortage of 2021, when Tesla was famously, reprogramming things on the fly to make these little chips work, and they were getting chips from different suppliers that had different code and all of that kind of stuff, and other manufacturers weren't able to do that, that was because Tesla has so much software engineering expertise, including a lot of people who program really, really well in C, because if you're going to do very, very high speed neural network inference engines, you have to use C. You have to get down into a lower level language that is able to operate at extremely high speeds. And so I would suggest that Tesla's engineers did have the capability to pull apart that code, look at it, reprogram these chips themselves, and put it back in again, which was the major advantage that they have. They didn't have to sit on their hands and wait for these companies to produce more chips, because they could go to another supplier that had somewhat different of a code base. They could reprogram it themselves and stick it into the car where they needed it. Plus the fact Tesla has fewer of these ECUs because they depend more on a centralized unit. They use the hardware 3 board for most of the work that needs to go on. So again, all of this leads to Tesla being far, far out in the lead, and it's because of the way the whole company operates, and because the company is really a technology company that happens to produce cars more than a car company that utilizes technology. And finally, let's watch a clip where Sandy and Tomas talk about the decision that most automakers are going to have to make very, very soon about whether they're going to do things themselves or let other people do it, and how under the hood they might actually be talking a little bit about Tesla.
I believe that every car company is, in the next 2 or 3 years, going to have to make a great big giant decision. And that great big giant decision is going to be, do we try and figure out, do we try and figure out how we're going to do this on our own? Or are we going to figure out how to use something that's in the marketplace that has tens of thousands of people basically working on their products? Are we going to do that? And if we do that, how many of these smaller chip companies are we going to leave in the dust?
I totally agree, Sandy. Yeah. I've been baffled. When I looked into the automotive industry starting around 2019, and I'm a software engineer and architect across many industries, but I looked into automotive and I found that the use of standard software in this industry is extremely limited. Think of it like, if you want a financial services system today to run your companies and HR systems, you're not going to write this yourself. You're going to use something from SAP, Oracle, and others in the market in there.
So as you heard, Sandy brings this up, and then Tomas agrees with this, that utilizing more standardized software solutions is definitely the way to go, especially if you have companies that are focused specifically on doing things. And that, again, that disaggregation, so you can buy hardware basically from anybody, and then you can buy standardized software. Again, it's the same sort of thing. If you want to use the Microsoft suite of tools or something, you could buy a Mac or a PC, and it runs on either hardware basically the same. And the ability to do that with ECUs, with all of these control units that are around, if you can have most of your compute on a centralized motherboard and then just a few of these ECUs around, and you can then suck the software out of these things and have that all done separately, especially if it's done by a team of people that are that's what they do. That's what they specifically work on. There are a huge amount of cost savings over repeating that from every single company. And of course, interestingly enough, this really actually fits with the legacy auto model. They like to purchase things from other companies and then put them together. So this is another layer of that. But I think the really intriguing part here, and something they didn't say, but I think was sort of a wink, wink, hinted at sort of thing, is Tesla's work on full self-driving. So consider how much money Tesla has spent and how brilliant their engineers are and how much data they have and how their fleet of vehicles is, has cameras and radar and ultrasonics and all of that kind of stuff to collect data for a decade now that other companies simply don't have access to. So they need to take 5 to 10 years, outfit all of their cars with expensive stuff, and then utilize that and put together a really amazing team to be able to solve full self-driving. Or what they can do is they can license things from Tesla. So Tesla becomes the developer. They make the the full self-driving OS essentially, and then these other companies can put things on top of it to make it pretty and make it whatever they want. But basically, the underlying software would be from Tesla in that case. And I think that that's what they're hinting at without actually saying it. But Tesla, again, very different company. They're not like Legacy Auto. They're highly vertically integrated, and they're doing all of this work in-house. It's been exceptionally expensive and difficult for them. But if and when they solve this in the next couple of years, other companies, it would make no sense for these other companies to try to replicate this because it would take too long, cost too much money, and be too risky. They still might not be able to solve it. They might not be able to figure out what Tesla did. Now, they have a higher degree of chance because once you know where the destination is, it's a lot easier to figure out where you're going. Tesla is still winding, trying to figure out where that destination is. But even so, there's a good chance that these companies could still fail because they don't have the quality of engineers, or at the very least, the amount of money and time and all of that kind of stuff that they're going to need to be able to solve this. So in my opinion, what they're talking about here, again, sort of wink, wink, nudge, nudge, is that, if and when Tesla does solve full self-driving, the most prudent financial decision for pretty much every other auto manufacturer is going to be to license from them, which is going to hurt their pride and everything, but it's going to cost a lot less money. But it also means that Tesla could just be raking in the money on this, right? If they're charging licensing fees for every single automobile that's sold, as opposed to, there are 2 to 3 to 5 million vehicles sold over time. If they're looking at maybe selling that on 50 or 60 million vehicles, right? Suddenly you're looking at 20, 30, 40 times the amount of vehicles that Tesla is selling currently. They could get licensing fees from all of those without really a ton of extra work because it's software. So obviously they would have to adjust things based on different vehicles and all of that kind of stuff. So there would be some cost, but you'd be looking at very, very high profit margins for this incrementally. And of course, Sandy and Tomas go on and talk about a whole bunch of other stuff, including things like child safety, which is really, really interesting, and how AI is going to hopefully help that situation where children get locked in the car accidentally in the summer and suffocate, overheat because of the heat, that you can use interior cabin cameras along with AI to try to solve that problem. So anyway, they get into a whole bunch of stuff. I highly, highly recommend watching the entire video, but I wanted to pull out those few things to really get into them a little bit more and explain, number one, why Tesla is so far ahead of the competition in this whole software, hardware area, and number two, why companies are going to most likely license from Tesla after they solve full self-driving. All right, I hope you enjoyed this episode and found it fun and interesting and thought-provoking. If you did, please do like it so other people can find it, because that's how YouTube's AI algorithm works. And of course, consider subscribing for more of this kind of content. In fact, it is my birthday this weekend, and as a birthday present, a really, really cheap and easy birthday present you can give me is just clicking the subscribe button and maybe clicking the bell icon or something like that. So thank you. And of course, as always, a huge shout out to my patrons on Patreon. Thank you all so much for your support. I truly do appreciate it. It's been a wonderful 2023 so far. And of course, if you want to join the team, just check out the link in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, Success is a Possible Outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on and on. So check it out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.